We're going to be looking at Taylor series this section, and it also follows true that when we were working with Taylor polynomials from the previous section, we're just going to keep building on that. So let's go ahead and review Taylor polynomials real quick, and we'll also put down the formula that we use for Taylor polynomials. And you'll also want to have your formula sheet of all the different series tests as well. So remember, for Taylor polynomials, if a polynomial if a function f has n derivatives centered at c, then the polynomial, and this is the formula that we want here, Pn of x is equal to f of c x minus c to the 0 over 0 factorial plus f prime at c x minus c to the first over 1 factorial plus f double prime at c second derivative evaluated at c x minus c to the second over 2 factorial, and this goes all the way up to the nth derivative x minus c to the n over n factorial. Then this is called the nth Taylor polynomial. Now, in order for this to occur, all the derivatives must exist here, and I need to be able to evaluate each of those derivatives at the center. Now, if this is centered at 0, if our c value is equal to 0, then this is called a Maclaurin polynomial. And you will see that quite a bit in this assignment. So a Maclaurin basically means a Taylor with the center at 0. So I don't have to rewrite this whole formula. I guess I could, it won't take too long. But basically a Maclaurin polynomial is a Taylor polynomial with c equals 0, so centered at c. So the way that this would look, and I could call it Pn again, is going to be equal to f of c x to the 0 over 0 factorial, because I don't have x minus 0 is just x, plus f prime at c x to the first over 1 factorial, second derivative evaluated at c, x to the second over 2 factorial, fn of c x minus c to the n over n factorial. So that's a Maclaurin polynomial. We're also going to be using some tables that will show up in the problems, and I'll show you what those look like when we get a little bit closer. But the thing to remember here is, in order for this to work, these Taylor polynomials, what I want to have happen is I need to be able to take all of the derivatives. So if I want to have a fifth Taylor polynomial, I need to take all the derivatives that apply to that, and I need to evaluate all the derivatives at c. If any of them are undefined, then this does not apply. So what we're going to do here is we're going to keep working on the polynomials that we used to, and then we're going to develop this and look at this in terms of looking for patterns and developing this into a series. Then we'll check for the series to converge, diverge, interval of convergence, and radius of convergence as well. So let's go ahead and get started just by looking at some problems. So this first problem that we're looking at asks us to do 3 things here. So first of all, find the first 4 non-zero terms. So let's say the first term happened to be 0. You would need to keep going and find the first 4 terms that don't have a 0 in them. And it says we're using a Maclaurin series, so right away I know that the center is equal to 0. This is the function we're given below that we're going to be working with. Then what we want to do is look at that pattern and see in part B if we can develop a power series, and then take that power series and check it and find intervals of convergence using either the ratio or the root test. So let's go ahead and get started with part A here. In order to find the first 4 non-zero terms, we need to look at a few things. We need to look at the derivatives, the center, and what they evaluate at. And then we can write out those terms. So first of all, let's go ahead and start with the original function. Original function is 2e to the negative 2x. The second derivative is going to equal negative 4e to the negative 2x. That's because the derivative of e to the u is e to the u prime. U prime in this case is negative 2, so I take negative 2 times the 2 out front to give me the negative 4. Second derivative, I'm going to do the same thing again, and I'll get 8e to the negative 2x. Third derivative would be negative 16e to the negative 2x. So first of all, right now I see that this is alternating. So I have, looks like a positive, negative, positive, negative. Now for each of these, the center is at 0, so x is equal to 0 for each one of these. E to the 0 is 1, so I just have 1 times the coefficient. So it would be 2, negative 4, 8, and negative 16. So if you notice, these are the first 4 non-zero terms, and I had to go to the third derivative to find that. So we don't always look at this automatically and think, oh, 4 terms, 4 derivatives. It doesn't always work like that. It depends on which are zeros and if you count that first term. Okay, so first 4 non-zero terms. So that would mean my P4 of x for this particular case. Actually, it's not going to end up being P4 of x. Let's look at this. I'll fill that in a second. We'll explain. It's going to be P3 of x. But this is going to be 2 x minus 0 to the 0, but that's just x over 0, x to the 0 over 0 factorial, minus 4 x to the first over 1 factorial, plus 8x squared over 2 factorial, minus 16x cubed over 3 factorial. So simplifying, and if you look at our highest power here, it's going to be 3. So P3 of x is what this is going to look like. Because I'm looking for, again, those first 4 non-zero terms, but my first term is a constant. So P3 of x is going to equal x to the 0 is 1, 0 factorial is 1, so 2 minus 4x plus 2 factorial is just 2, 8 divided by 2 is 4, so 4x squared, minus 3 factorial is 3 times 2 times 1. 2 goes into 16 8 times, so I'm left with 8/3 x cubed. So those are the first 4 terms of the Maclaurin series of f of x equals 2e to the negative 2x. So that's part A. Let's go ahead and look at part B next. Now for part B, I'm going to rewrite this again I'm going to spread it out a little bit because I want to be able to talk about these terms. Now when I write my power series, I'm going to start with the indice k equals 0. So this first term, I want k to equal 0, k equal 1 for the second, k equal 2 for the third, and k equal 3 for the fourth. So that's what we have here. Okay, so now I also notice that they're alternating. So I have quite a few things going on here. If it's alternating, I need to have some sort of a component that produces that alternating part. So it could be a negative 1 to the k. If k is 0, negative 1 to the 0 is a positive 1. K equal 1, negative 1 to the first is a negative, so that produces that sequence. And I don't know if I'll keep it like this. We'll see if we can do anything else with it, but that's a good place to start. Now, as we look at this, my exponents, if I wrote this as x to the 0, I could start over here and call this x to the k. So x to the k would produce x to the 0, x to the first, x squared. So what I have here is I have the x to the power, I have the positive negative alternation, but what I don't have is the 2, 4, 4, 8/3, etc. And then also it looks like to me I'm going to need a denominator here at some point. So what we want to do is we want to look back just up a little bit where these originally came from right here. So it looks like before I simplify that, this just came from the k value factorial. So 0 factorial for the first term, 1 factorial for the second term. So this is just k factorial. So now it looks like we're getting a little bit closer. I have the denominator I need. Now let's look at that 2. So it goes 2, 4, 8, 16 for my coefficients. Well, those are just powers of 2. So as I look at those powers of 2, that's 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So it looks like to me my powers are always 1 higher than my k value. So again, this is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth was right here. 2 to the fourth was 16, of course, and that simplified and reduced down to 8/3 when I used the factorial with it. So what this is going to look like then is 2 to some power, but it's always going to be the value of k plus 1. So plus 1 more term. So that's one way we could write it. Let's see if we can simplify that a little bit. So as we go through and simplify this, I'm going to split these up a little bit. So I have the -1 to the k. 2 to the k plus 1 is 2 to the k times 2 to the first. And then I have this x to the k all over k factorial. Well, a couple things I see here. I could combine these two. When you multiply like bases, you add exponents. I don't have like bases here for this. However, I could combine these into the same base because they have the same exponent. So I could rewrite this as k equals 0 to infinity, and this would be a -2 to the k, and then I have this 2 to the first, which is this 2. I can pull that out front. That's nothing to do, this 2 is nothing to do with the exponent on the k. And then I have x to the k all over k factorial. So this is rewritten and combined as much as possible. I'll leave the x to the k out of this right here because it is x is going to be what I want to force to converge. It's a constant. So let's go ahead and call that our answer for part B. And there's many ways that you could simplify it, but the important thing to remember is it has to simplify and produce the series that we're looking at. So my next step is I want to find the interval of convergence. Now this has a factorial in it, so I'm going to use a ratio test on this one. So you have to look at each one individually and decide ratio or root test. So I always name my test, and then I talk about the terms of the test. R is equal to the limit as k approaches infinity of the absolute value of our next term. So it would be 2 times -2 to the k plus 1, x to the k plus 1 all over k plus 1 quantity factorial divided by my current term. My current term is going to be 2 times -2 to the k, x to the k all over k factorial. So simplification here, lots of algebra. When you divide by a fraction, you multiply by the reciprocal. So here I'm going to have 2 times -2 to the k times -2 to the first, x to the k, x to the first. So I'm splitting these up, and this would be k plus 1 factorial. Now remember, k plus 1 factorial is really k times k factorial. And then this would flip, so I'd have a k factorial on top, 2 times -2 to the k, x to the k. So note, k plus 1 factorial is k plus 1 times k factorial. So what will cancel here? Well, the k factorials cancel, that's why we rewrote it. These 2's cancel, a -2 to the k cancels, and an x to the k cancels. So let's see what we have left. So r is equal to the limit as k approaches infinity of, looks like we have -2 to the first, so that's -2, and then I have an x left on top all over k plus 1. Now I can pull the absolute value of -2x out front because it's a constant. The variable here is k. 1 over k plus 1. K is always positive, so I don't need the absolute value signs there, but I do need them around the -2x. Now this term is going toward 0 because the numerator is fixed, the denominator is increasing without bound, so that's going to 0. negative 2x, sorry, the absolute value of negative 2x times 0 is equal to 0, which is less than 1. And if you look at your ratio test, that's going to converge absolutely for all x. So I don't have to force this to converge. It converges absolutely for all x. Because this is less than 1, this is 0, which is less than 1. There's nothing I can change here for the x values to get this to be any other value than 0. So my interval convergence, because it converges for all values of x, is from negative infinity to infinity. And I don't need to check the endpoints here, because if my endpoints are infinity, I can't check them because they're always going to have parentheses. They'll never have a bracket. So for this problem, we're doing the same thing again, except we're given a different function. We're looking at the first 4 non-zero terms of the Maclaurin series, so we know right away we're centered at 0 for this function, and the function that we're given is natural log of 1 plus 6x. So we might have some simplifications to do here, but let's go ahead and get started with, first of all, the derivatives, the center, and what it looks like when it's been evaluated. Now I left a little more space than usual under derivative just in case I need more space to calculate these. So f of x is my original function, so that's a natural log of 1 plus 6x. F prime of x, the derivative of the natural log of u, is 1 over u. So that's 1 over 1 plus 6x times the derivative of 1 plus 6x, which is 6. Okay, and remember my centers here are at 0, so x equals 0. So if I let x equals 0 in this first term right here, 6 times 0 is 0, 1 plus 0 is 1, the natural log of 1 is 0. So my first term evaluates at 0, so I don't get to count it because it says the first 4 non-zero terms. So let's look at our second one, 6 over 1 plus 6x. So if x is equal to 0, then I have 6 times 0 is 0, 1 plus 0 is 1, 6 divided by 1 is 6. So there's my first non-zero term. Now when we go to take the second derivative, what I want to think about is rewriting this. You could use the quotient rule on it, but I think it might be a little more work. If we flip that up top, I can just use a chain rule. So to use a chain rule, I'd bring the negative 1 down, decrease the exponent by 1, so it'd be a negative 2 there, and then multiply it by the derivative within. So the derivative of 1 plus 6x is 6. So simplifying, this would look like negative 36 over 1 plus 6x quantity squared. Now if I plugged in x equals 0, 6 times 0 is 0, 0 plus 1 is 1, 1 squared is 1, negative 36 over 1 is negative 36. So we have 2 non-zero terms now, so I need to keep taking derivatives. I'm going to flip this up top again, so I can go ahead and use the chain rule again for my third derivative. So from here what I would do is I would have the negative 36 out front, I'd bring the negative 2 down, decrease the exponent by 1, so negative 2 goes down to negative 3, and then I multiply it by the derivative within, so the derivative of 1 plus 6x is 6. So if we look at our coefficients here, I have some positive and negative values. So it looks like I have a negative 36 times a negative 2, which would be a positive 72. And I have positive 72 times 6 would be 432. So I have 432. And then that 1 plus 6x flips down into the denominator. It is a negative 3, but when it flips it becomes a positive 3. Now if I evaluate this at 0, I'm going to get 6 times 0 is 0, 0 plus 1 is 1, 1 cubed is 1, so 432 over 1 is 432. And again, I'll rewrite this before I take my next derivative. So I have 1 zero term, then I have 1, 2, 3 non-zero terms, so this should be my last derivative. So my fourth derivative. So I have a 432 out front. I bring the negative 3 down, decrease my exponent by 1. So that's going to go to negative 4. And then I multiply it by the derivative within. The derivative of 1 plus 6x is 6. So simplifying here, I'll have 432 times that negative 3 times 6. And I get negative 7,776. And then from there, I can rewrite that exponent by flipping it into the denominator. So that's going to be 1 plus 6x to the 4th. Now I don't need to flip this up top, because if I flip it up top, that means I'm going to take another derivative, and this will be my 4th non-zero term. Notice the denominators are always going toward 0 when I plug a 0 in, so the next term is negative 7,776. Well, I still don't have my solution here. I still want to write this in summation notation and find my terms. So using a Maclaurin series, remember that means centered at 0, that's going to look like p of x is equal to 0, would be this first term. I know we don't need it there, but I'm going to include it just so we can see what's happening here with our other terms. Plus 6x to the first over 1 factorial minus 36x squared over 2 factorial plus 432x cubed over 3 factorial minus 7776x to the 4th over 4 factorial. So simplifying this whole term, this first term goes to 0, but I put it in there so it helped me keep track of my powers and my factorials in the denominator. So as we simplify, let's see what we get here. So I get p of x equals six x to the first over 1 factorial. 1 factorial is just 1, so this is going to look like 6x for my first non-zero term. Next I'll have 36 divided by 2 is minus 18x squared. Now 432 for my next term is divided by 3 factorial. 3 factorial is 3 times 2. And if we divide it by 3 times 2 or divide it by 6, I get plus 72x cubed. And then lastly here, we have 76 divided by 4 factorial. Now remember, 4 factorial is 4 times 3 times 2 times 1. So you take negative 7776 divided by 4, get your answer, divided by 3, get your answer, divided by 2, get your answer. Or if you want to just divide it by 24, that works as well. And you get minus 324 x to the 4th. So those are the first 4 terms. Now part B would like us to see if we can find a pattern here to rewrite this series. So right away, when I'm looking at this, I see quite a few patterns popping up. I would like to go to my pre-simplified though up here. Right away I see in my denominator I have k factorial, 0, 1, 2, 3, that progression. If you see your exponents 0, 1, 2, 3, 4, that's going to be x to the k. So I have a little bit going on here. I also have this alternating positive, negative, positive, negative. So that would be a negative 1 to the k. But what I don't have is this 6, 36, 432, 77, 76. That is not as easy. So let's try and figure out where that comes from. Well, when I move from 6 to 36, that's 6 to the first. That's 6 squared. So let's see if this keeps increasing like we would expect. And you would think this pattern would continue, and you would think that this would be 6 cubed then, and this would be 6 to the 4th, but that's not true. 6 cubed is going to be equal to 216. But we know that 2 times 216 is 432, so that's interesting. Now 6 to the 4th, that is not equal to 7776. 6 to the 4th is going to be equal to 1296. But if I take 1296 times 6, I'm going to get that 7776. But let's think about what 6 is. 6 is equal to 3 times 2. So this is equal to 3 times 2. This is equal to 2, so I could call this 1 times 6 squared, and this would be 1 times 6 to the first. So I kind of am seeing a pattern here. This almost looks like a factorial here a little bit. The 1, 2, 3 times 2 times 1. So let's see how we could rewrite it using that. So rewriting up here then, I'd have 2 times 6 cubed. Here I would have 3 factorial, or 3 times 2 times 1 times 6 to the fourth. This is interesting. So now let's incorporate these factorials. So I'm kind of running out of space here. So that would be 1 factorial, 2 factorial, 3 factorial, 4 factorial. So I'm looking at this and it almost looks like these numerators might start canceling with some factorials in the denominator. It almost looks like the numerator has one less product in the factorial. So for instance, this numerator right here has 3 factorial, the denominator has 4 factorial. This numerator has 2 factorial, this has 3 factorial. This has 1 factorial, this has 2 factorial. And this of course would be 1 factorial and 1 factorial if you want to think about it like that. So I'm thinking that a lot of things are going to end up canceling here, and I'm not going to need this factorial down here. So let's keep trying to rewrite this a little bit to try and get this into the correct form. I think we're getting pretty close. I want to ignore this entire first term, so instead of starting with k equals 0, let's start with k equal 1 instead. I think that'll make it easier because this whole first term goes away, so we don't really care. Here we're starting with 1. So I still have this x to the k, that makes sense. And it looks like to me I still have the 6 to the first, 6 to the second, 6 cubed, 6 to the fourth. So that would mean I'd have a 6 to the k. Now negative 1 to the k is not going to work anymore because I need to start this with a positive first term. So that would be negative 1 to the k plus 1. And that's going to start off my first term as positive and then alternate from there, positive, negative, positive, negative. So I have negative 1 to the k plus 1, 6 to the k, x to the k, and then I have this k factorial. But look what happens here. The k factorial, everything ends up canceling except for the first term of the factorial. So here, this is 3 times 2 times 1. The 2's cancel. This is 4 times 3 times 2 times 1. The 3 and the 2 cancel, so I'm always just left with this first term. So instead of a factorial, I think we're just left with a k here. So let's rewrite this again and see if it works. And this is a trial and error process, and you're not always going to get it exactly right the first time. You just have to kind of be willing to spend some time on it to see what you can get figured out. All over x, and then times x to the k. So k equal 1. So negative 1's quantity squared is positive, so that's correct. 6 to the 1 is 6, that's correct. X to the 1 is x, so that's correct. K equal 1 is k is 1 in the denominator, that's correct. And you can go through and check these one by one, but this is our series. And again, there could be more than one way to write that, but that's where we're going to start. Now let's go ahead and find part C. I can't even remember on this one. Were we supposed to find an interval of convergence? So let's go back up and have a look. So yes, it does look like we have an interval of convergence. So let's go ahead and write down that work. So we want to find C, our interval of convergence. So our series then, up here, I could start with the ratio test. Always name your test. And then show what the criteria of the test is. K goes toward infinity, the absolute value of the next term. I can just drop all of these negative 1 to the k plus 1's and everything because I'm taking the absolute value, so they're all going to turn out to be positive. So this would be 6 to the k plus 1 times x to the k plus 1 all over k plus 1. And this is the next term divided by the current term, and the current term would be 6 to the k all over k times x to the k. And I'm going to pop this x to the k into the numerator, so when I flip it, it'll be easier to see what's going on there. Now remember, when you divide by a fraction, you multiply by the reciprocal. So I'm going to rewrite this as 6 to the k, 6 to the first, x to the k, x to the first, all over k plus 1, times k flips up top, then I'm left with 6 to the k, x to the k when I flip that. Now in terms of canceling, the 6 to the k's definitely cancel, the x to the k's definitely cancel, and it looks like I'm left with 6xk on top. So this is going to be equal to the 6x I can pull out front, and it's in an absolute value. And then I'm left with the limit as k approaches infinity, and then I'm left with k over k plus 1 in the argument of my log. Well, this is going to be equal to 1 because the degree in the numerator and the degree in the denominator are the same. So what I get here then is absolute value of 6x, and I want to say that this is less than 1 because I want to force convergence for the ratio test. So this forces convergence. So what I can do here then is I can rewrite this in interval notation using the definition of absolute value. So -1 less than 6x less than 1, divide through by 6, and I get -1/6 less than x less than +1/6. So this is my interval of convergence until we have to check the endpoints. So you always have to remember to check the endpoints. So I'm going to go ahead and check endpoints. You always have to do this unless it's a point convergence where it's only converging at a single point, or I don't have to check it if I'm going from negative to positive infinity because I can't check the endpoints for infinity. So let's go ahead and check x equal -1/6 and x equal +1/6. If I check x equal -1/6, let's scroll up a little bit, I'm checking right up here in my original series. So I'm checking the series -1 to the k plus 1, 6 to the k, and then I have x to the k, but x is a -1/6 to the k, and then this is all over k. I'm going to go ahead and write this one out here as well. So this would be -1 to the k plus 1, 6 to the k, +1/6 to the k, all over k. Now I'll test these separately. I just wanted to get those written out. Okay, so simplifying here, I definitely have the -1 to the k, -1 to the first, 6 to the k. So I think I can simplify this if I split this up a little bit. -1 to the k, -1 to the first, 6 to the k, and then here I'm going to rewrite this as -1 to the k. And then in the denominator, I'm going to rewrite this as 6 to the k all over k. So this is what I split up down here. Now let's see what cancels here. So it looks like the 6 to the k's cancel, and then the -1 to the first is just a -1, so that's just a negative. It also looks like I have a -1 to the k times a -1 to the k. When you multiply like bases, you add exponents, so k plus k is 2k, which is always going to be positive. So these end up not canceling, but these always will produce a positive value. So let's see what we're left with. Looks like in the numerator, I'm left with a -1 over k. Well, this is a p series. I could pull the negative out front if it helps you recognize that a little bit more. This is negative out front, 1 over k to the first. So this is a divergent harmonic p series. So this is p equal 1, and then if you look on your sheet of tests with this p series, if p is less than or equal to 1, it diverges. So that means when I write my interval of convergence, on the left-hand side I'm going to have a parentheses because I don't have a convergence at -1/6, I diverge. Now let's go ahead and check everything on x equal 1/6 now. Let's see what we can rewrite here. So I still have my summation. I'll have a -1 to the k, a -1 to the first, 6 to the k, And then I have this 1 to the k all over 6 to the k times k. And again, this is rewritten 1 to the k in the numerator, 6 to the k in the denominator. Now our hope is here that lots of things cancel, and some things do. So I have a 6 to the k and a 6 to the k that cancel. 1 to the k is just going to be 1. And then here I could recombine these since nothing ended up canceling, so that wasn't very exciting to split those apart. So I have negative 1 to the k plus 1 all over k. Now this is not a p-series anymore because it's alternating. So this is the alternating series. So I'll use the alternating series test. So there's two criteria for the alternating series test. The first criteria is it has to be decreasing if we just look at the 1 over k part. So the series 1 over k terms are decreasing. Now remember, I could just do a comparison there, or I could take a derivative. So the derivative of 1 over x is equal to negative 1 over x squared, which is always less than 0. So therefore that establishes decreasing. And the second thing I need to show is if I take the limit as k approaches infinity of 1 over k, I have to equal 0. So check, because these two both work, this converges. So my right endpoint does have a bracket because it converges. So this is my interval of convergence. Left endpoint is parenthesis because it diverges. Right endpoint is bracket because it converges. So this is a pretty long problem, and it was very tricky. I think the trickiest part here is when we came up and we were kind of using trial and error trying to figure out how I could rewrite this in series notation from here down to here. And the key to that was coming up and looking at the pattern, I think, in these coefficients. So right here I can see I had a 6, and then I had a 6 times 6, and then I had a 6 times 6 times 6 times 2, and then here I had that 6 out front, of course, and then I had the 3. So that kind of helps us try and determine what's going on here when I'm trying to figure these out, is by looking at these coefficients. So keep track of that. It'll help you kind of try and figure out some of these that are a little bit more difficult to rewrite. And it's trial and error. You're not going to get it right the first time. Sometimes you're going to have to change your indices, and sometimes you have to change your values. But the key is to keep checking and making sure that it's producing the series that you think. Our next function is going to be f of x equals 1 over x that we're working with. And it says to complete parts A and B below. So I'll fill in those parts as we go. For this one, we want the first 4 non-zero terms for part A. And then for part B, we want to find a series that produces the particular sequence that we have. So we'll work on the first 4 non-zero terms first. So we need derivatives. And I'm going to leave a little extra space here. We need our center. And our center here is at c equal 3 or a equal 3. Not sure how many we're going to need here. And then we'll look at how this evaluates. Okay, so let's start with our function. So f of x equals 1 over x. If I evaluate that at x equals 3, I get 1/3. I can rewrite this as x to the negative 1, which will make it easier when I take the first derivative. So I'd bring the negative 1 down, decrease the exponent by 1. So I would have negative 1, let's write that here, negative x to the negative 2. And if I rewrite that, f prime of x then would be negative 1 over x squared. If I plug that in with a 3, I get 3 squared is 9, so I get a negative 1/9. So the second derivative, I'm going to use this piece right here. I have a negative out front. I bring a negative 2 down. So a negative times a negative is a positive, so that's 2x to the negative 3. And then rewriting to make this a little bit easier to evaluate the second derivative, I get 2 over x cubed. Plugging in a 3, 3 cubed is 27, so I get 2 over 27. This might be alternating. So let's look at the third derivative. 1, 2, 3. And I'm going to use this piece or that rewrite so we can figure out what's going on here. So I bring the negative 3 out front. So 2 times negative 3 is negative 6. Decrease the exponent by 1. And then to make that easy to evaluate, let's rewrite that as negative 6 over x to the fourth. So if I plug a 3 in there, I'm going to get a negative 6 over, and then 3 to the fourth is going to be 3 times 3 is 9 times 3 is 27 times 3 is 81. But this reduces because both the 6 and the 81 are divisible by 3. So negative 6 divided by 3 is a negative 2, and then 81 divided by 3 is 27, so that reduces. So those are my first 4 terms there. Now let's look to see what we have next. Now I shouldn't say these are my terms, these are my coefficients. So now what I'm going to do is to go ahead and plug this into the formula for a Taylor series. So I'm going to have f of 3 times x minus 3 to the 0 over 0 factorial. I'll just write out a few of these so you know where they come from. F prime of 3, x minus 3 to the first over 1 factorial. Second derivative evaluated at 3, x minus 3 squared all over 2 factorial. And then the next one would of course be the third derivative evaluated at 3, x minus 3 cubed all over 3 factorial. Okay, so let's fill in what we know here. So f of 3 was 1/3. That came from right here. X minus 3 to the 0 is 1. 0 factorial is 1, so I just get a 1/3 here. F prime of 3 is negative 1/9, so I have a negative 1/9 times x minus 3 to the first, which is just x minus 3. 1 factorial is just 1. Okay, plus 2 over 27. That comes from right here. X minus 3 squared all over 2 factorial. So there's some simplification that we can do there. Minus, that's going to come from right here, 2 over 27, x minus 3 cubed over 3 factorial. So again, there's some simplification that we can do here, and let's go ahead and do that before we try and write this in series notation. And when we write it in series notation, sometimes it's more helpful to go back to this version to see what's going on. So we have a 1/3 minus 1/9 x minus 3 plus, now 2 factorial is just 2 times 1 or 2, so these cancel, so I'm left with 1/27 x minus 3 quantity squared. Next, 3 factorial is 3 times 2 times 1, so the 2's will cancel here, and so I'm just left with minus 1 over 81. 27 times 3 is 81, x minus 3 cubed. So these are the first 4 terms of this Taylor series. So next what we want to do is we want to try and rewrite this in summation notation. So our summation notation here is going to start, I think, with k equals 0, and maybe we'll adjust it. Now we know we have the alternating part, so we're going to have to take that into consideration. So I'm going to have a negative 1. It starts positive, so I could just go negative 1 to the k here. And then I definitely have an x minus 3 on each of these. And it looks like this is x minus 3 to the 0, x minus 3 to the first, second, third, so that looks like it could be x minus 3 to the k. And then in the denominator, it looks like I just have powers of 3. So here I'm starting with 3, 3 squared, 3 cubed, 3 to the fourth. But if I start my indice at k equals 0, this is going to be not just 3 to the k, because 3 to the k would give me 3 to the 0 is 1. I need a 3 there, so it has to be k plus 1. So this is my series that I can write that will produce this, in not just the first 4 terms, but all the terms. Now I could check it for convergence or divergence, or sorry, convergence, interval of convergence, radius of convergence, but this particular problem doesn't ask us to do that. This next one is going to ask us for the parts A and B to be the same here, but they give us a different function. So for part A, we're looking for the first 4 non-zero terms. So we're going to have to start with derivatives and then work from there. So let's look at our table here. Derivatives, and then our center is at a equal 3 or x equal 3. And then we'll look at this in terms of evaluating these, plugging into those derivatives. So let's go ahead and start with f of x equals 7 ln of x. F prime of x would be, derivative of the natural log of x is 1 over x, so that would be 7 over x. I could rewrite that as 7x to the negative 1. That'll make it easier when I take the second derivative. I'd bring the negative 1 out front, decrease the exponent by 1, so that's negative 7 over x squared. And then let's do third derivative, and it looks like all of these are going to be non-zero, so this should be where I could stop here. So I'm going to have 14x to the negative 3, which is the same as 14 over x cubed. So we're going to evaluate each of these at x equal 3, which is the center that they gave us. So if I plug in x equal 3, I get 7 natural log of 3. That doesn't simplify anymore, so I leave it like that. Then I have 7 over x, so that would be 7 over 3. Here I'd have negative 7 over 3 squared, so negative 7 over 9. And then I have 14 over 3 cubed is 27. So these, I don't really see a really big pattern here that's easy to tell. Hopefully when I start looking at these terms, it's going to be a little bit easier. I almost think that this one is not going to fit in anywhere, so I'm going to start with that term and then I'll start my series. So for part B, let's use that strategy. So my series is going to be looking like 7 natural log of 3 plus, now let's go ahead and start the series. And the reason is I'm not going to be able to fit in this 7 ln of 3 anywhere. So we could start at k equal 1 or 0, and then maybe we'll have to adjust. And again, it's trial and error. For this one, let's go ahead and start at k equal 1. Now if I start at k equal 1, I notice that I have 7, and again this is where k equals 1, k equal 2, k equal 3. I notice that I have 7 and then I'm alternating, so I have positive, negative, positive. So I'm going to be alternating here. My first term is positive, so I would start with a k plus 1 here since I'm starting with k equal 1. And then the denominator. The denominator I think will be pretty straightforward. It looks like 3 to the first, 3 squared, 3 cubed. So that's just 3 to the k. Okay, so now we need to talk about these numerators. So we got the alternating part, we have the denominators. Now let's try and figure out the numerator. So for the numerator, it looks like I have 7, 7 times 2, 7 times 1, 7 times 2 for 14. So there's definitely a 7 involved here. Now the problem is, what am I going to do? You know what? I forgot to do something here. I just kind of skipped this part, but there should be an x minus 3 to the k here. So let me move this down and I'll write that out real quick. And what that is I found all the coefficients, but I didn't actually write out the Taylor polynomial. So let's do that real quick. So p of x is going to be equal to 7 natural log of 3 x minus 3 to the 0 all over 0 factorial plus 7/3 x minus 3 to the first all over 1 factorial minus 7/9 x minus 3 squared all over 2 factorial plus 14 over 27 x minus 3 cubed all over 3 factorial. Okay, so that's what I'm trying to produce here. So I forgot that in the first part, and that'll help us rewrite here in the second part. So that's where the x minus 3 to the k is coming in. And actually, let me move this down a little bit more. We'll simplify that a little bit. So I'd get p of x equals 7 natural log of 3 plus 7/3 x minus 3 minus the 2 factorial is just 2 times 1 or 2. That doesn't cancel into the numerator, so it's just going to be 7/9. It's a negative x minus 3 quantity squared. Now here something will cancel. So 3 factorial is 3 times 2 times 1. So this 2 will cancel into the 14 7 times. So I'm left with 7 over 81. 27 times 3 is 81. X minus 3 cubed. So I just forgot to put it in the Taylor polynomial form, and I just found the coefficients and then moved on. So let me move this back up. And now let's see if we can rewrite that in series form. Okay, so I still have the 7 ln of 3 as my first term. So that still comes from here. And then I'm still alternating. I'm starting positive and then negative, then positive. So that's working here. I have the x minus 3 to the 0. I'm going to ignore that. So x minus 3 to the first. So I can start with 1, 2, 3. That's working. So it looks like the 7 is what's kind of throwing me off here. So when I'm looking at the 7, I have a 7, 7, 7. So it looks like to me all of these are just a straightforward 7 in the numerator. So I'm going to keep that as a 7. I don't have to worry about powers because up here some of those factorials canceled. However, let's look to see what we have here. K equal 1 to infinity. 3 to the first is 3. 3 squared is 9. 3 to the fourth is 81. So that's my problem here. So this is 3 to the first, 3 squared, and then all of a sudden I jump up here to 3 to the fourth. So those are not going evenly into those powers increasing by 1. So I'm going to have to compensate for that. And as I'm looking at this, right here, this 9 times 2 should have been 18. So let's change this to an 18. So this is going to be 2 times 3 squared. So this is going to be 1 times 3 to the first, 2 times 3 squared. This would be 3 times 3 to the fourth, and then, or sorry, 3 times 3 cubed. Then it's going to follow those indices to equal 3, 18, and 81 if I put a 3 down here in front. Okay, so I had a little error there. The 7 times 7 over 18 was difficult to find because I had a mistake, and once we saw that, we can see the pattern of the 3, 18, 81. So I have that 1, 2, 3, which is just the value of k. So I can replace that with k. So this is my series notation. And of course, there could be other ways to write it. That's just how I have this one written. So when you're working with these, it's trial and error. Always go through and check. And if it's not working out like you think, maybe you have a mistake like I did there. So look for your mistakes and see if that will work out a little simpler. Now, there's a lot of patterns in all of these problems that we've been doing, and using these tables of Taylor series really shortens up these problems. For some functions, we have a predictable set here. We could go through and take the derivatives and write our series ourselves, but some of the problems in my math lab go through and they say, well, these are always turning out the same, so let's just use this table to summarize these. Now, this problem, natural log of 1 plus 3x right here, looks most like this one at the bottom. It's not natural log of 1 plus x exactly, it's natural log of 1 plus 3x, but I can rewrite this a little bit. So what we do here is we say, okay, we have the natural log of 1 plus 3x, and in my table, the closest thing I have for that is the natural log of 1 plus x. So what that tells me then is for each value of x in my formula, I have to replace it with a 3x. So I'm going to replace x with 3x. So I'm going to go ahead and come down here and pull these values. So the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3. And let's just go ahead and write out one more term. I think it's going to alternate. So we're going to have minus x to the fourth over 4. So if I went through and I did the derivatives and evaluated this at 0, so this is really a Maclaurin series, then what happens here is this is what I'd come up with. So they've shortcutted the process and said, well, let's just look at this table, and in this table we can look at these shortcuts. Now, how can we make this fit with what we have? So we have the natural log of 1 plus 3x. So everywhere there's an x, I'm going to put a 3x. So instead of just an x, I'll put a 3x. Instead of just an x, I'm going to put a 3x. Both of them are squared. you can't just write it as 3x squared. That's wrong. It has to be in parentheses 3x to the second minus 3x to the third over 3 minus 3x quantity to the fourth over 4. So if you just write it as 3x to the fourth, that's wrong. It has to be the quantity of 3x to the fourth. And then you can rewrite this if you want to see if anything will simplify. And I have 3x. And I think in my math lab they rewrite these as powers, so they rewrite this as 3 squared x squared over 2 minus 3 cubed x cubed over 3 minus 3 to the fourth x to the fourth over 4. And of course this pattern would continue on. So if I make that substitution, that makes this process a whole lot easier. Now I could also come down here and I could just replace this x with a 3x, and that would be my summation or my series for me there. So knowing these tables are going to be very helpful, and they're actually in your problem set where it says click the icon to view a table. If you click this icon, you'll come up with this table over here. And it's actually longer. I just took a screenshot of everything up until the natural log of 1 plus x, which we needed for this problem. So let's try one more like that. So for this one, again, we're going to be looking at the table. When you come to this problem where it says click on the icon right here, let's try this again. Right here, click this icon and this table shows up over here. Well, the closest thing we have to the sign of 11x to the fifth here is the sign of x. So this is the line that we're going to use right here. So when we rewrite this, we want to take the sign of x, and it looks like x minus x cubed over 3 factorial. And again, we could come up with these on our own by taking the derivatives and evaluating them. And this is centered at 0, so it's a Maclaurin. So we can see that this is what's happening if we go through and take the derivatives in that process, but they're giving us this shortcut. So positive, negative, 1357 is my power over 7 factorial. So this is what's going to happen here. And what's I'm going to do now, instead of the x, I'm going to replace that with 11x to the fifth. So this would be the sign of 11x to the fifth. So what I'm going to do in this right here is I'm going to replace all x with 11x to the fifth. I'm just going to make that substitution. So let's go ahead and do that. So the sign of 11x to the fifth is equal to x. Well, I'm replacing x with 11x to the fifth minus 11x to the fifth quantity cubed over 3 factorial. Again, I cannot write this as just 11x to the fifth cubed. It has to be all of this cubed. If you don't do that, it ends up being incorrect because the cube doesn't distribute correctly. So 11x to the fifth over 5 factorial, and we wanted the first 4 non-zero terms, so we need to go one more, minus 11x to the fifth to the seventh all over 7 factorial. So those are the first terms, and I can see the pattern from right here, so I can continue that on. So from here, I think we could simplify this a little bit. So let's rewrite this as sign 11x to the fifth equals 11x to the fifth minus 11 cubed x to the 15th, because when I raise a power to a power, I multiply the powers, so 5 times 3 is 15, over 3 factorial, plus 11 to the 5th x to the 25th over 5 factorial, minus 11 to the 7th x to the 35th all over 7 factorial. So those are the first 4 non-zero terms. Now if I wanted to, I could come over here and replace this x with 11x to the 5th and then simplify and then test the series if I wanted to. But they're giving us this shortcut and just asking us to write out terms and not test for anything right now. So having these tables is really helpful, and they are in your homework problems just by clicking that icon that they're showing here. And if you click that icon, those pop up, so you'll have those available to you in those problems. The last two problems that we're going to do, we don't use those the table of Taylor polynomials, but they do give us the Taylor series off of that table for us. So what they do is they say use this Taylor series. So they don't have a table that you pop open, they just give you this summation right here. So let's go ahead and look at what they give us. They give us 1 plus x to the negative 2. So the quantity 1 plus x to the negative 2. Now if we compare that to what we have 1 minus 4x to the negative 2. So it looks like we would take x and replace it with negative 4x, because I need to make the 1 plus x convert into 1 minus 4x, so I could substitute the minus 4x in for the x. So what we're going to do then is we're going to take 1 plus x to the negative 2 equals 1 minus 2x plus 3x squared minus 4x cubed. And we're looking at the first four non-zero terms, so that looks like that does that for us. If it doesn't, we can keep going on and predicting those terms. So down here, when we rewrite that 1 plus x, or sorry, 1 minus 4x to the negative 2, that's going to equal 1 because there's no x to substitute in for, and then minus 2, and then in place of the x there, I'll put the minus 4x. And so all of these where we have an x, I'm going to replace it with the minus 4x. Just like that. And then we can simplify a little bit. Now all of these simplify a little bit differently. Some will simplify completely and some look like they don't simplify very far at all. So for this one, I think we do simplify a lot. So negative 4 squared, quantity squared, is 16 times 3 is 48. So this would be 48x squared. And then negative 4 cubed is negative 64. Negative 64 times negative 4 is positive 256x cubed. So those are my first four terms. So first, second, third, fourth. Okay? So that's an example of using that table again, but instead of giving you an entire table, they just summarize it right here. And they pick that line off the table that you need. Okay, last problem. So it's similar as setup as we had for the previous one. Instead of giving us the entire table of Taylor polynomials, they give us the value off the table that they want us to use. Okay, so we have a Taylor series centered at 0 for the function given below. So let's go ahead and look at what we have here. So I could take 9 plus 8x to the negative 2 and rewrite it if I flip that up top. And we're trying to make this look like 1 plus x quantity to the negative 2 as much as possible. So it looks like to me that we need to take the 9 that's in the first position and do something with that to turn it into a 1. So we could think about factoring out a 9, or I think factoring out a 9 would be our best bet. So let's look at it this way. So if I factor out a 9, I'm going to be left with 1 plus 8/9 x, and then all of this, so that's why I have big brackets here, is to raise to the negative 2. So if I take the 9 and redistribute it, I get 9 times 1 is 9. 9 times 8/9, the 9's canceled, I'm left with 8. Okay, so if I factor out a 9, this is what this looks like. So this would equal then 9 to the negative 2 times 1 plus 8/9 x to the negative 2. And now it comes really close to matching this, and it's just a substitution. So I'm going to substitute x for 8/9 x. So that's what we're going to have happen here. So let's go ahead and write it out. So from what they gave us, 1 plus x to the negative 2 is equal to 1 minus 2x plus 3x squared minus 4x cubed. And then when I rewrite this, I have 1 plus 8/9 x to the negative 2. And then I have the 9 to the negative 2 out front. So I have a 1/9 then times 1 plus 8/9 x to the negative 2. So what this is going to look like then is 9 to the negative 2 times 1 minus 2 times 8/9 x plus 3 times x squared minus 4 times x cubed. But remember what x is. I'm replacing that with 8/9 x in each of these positions. And I have the 9 to the negative 2 out front. So that's going to look like 1/9 out front. Now all of these seem like they simplify a little bit different. So we have to kind of be careful how far you go if you want to compare your solutions to what they have in my math lab. So let's just do a basic simplification. So let's leave this as minus 2 times 8/9 x, or we'll write it as 8x over 9, plus 3 times 8x over 9. And that's going to be, I think I dropped my squareds here. Yeah, this one's squared and this one's cubed, so this one's squared. And then I have minus 4 times 8x over 9 quantity cubed. Then I'll distribute through the 1/9, so I'll have 1/9 minus 2/9 8x over 9 plus 3/9 times 8x over 9 quantity squared minus 4/9 times 8x over 9 cubed. So our terms then, if you want to look at these, are going to be the first, second, third, and fourth terms. Now let's double check and make sure we don't have any mistakes here before we might simplify one more step. And I see a big mistake right away. So 9 to the negative 2 is 1 over 9 squared, which is 1 over 81. So that's going to change each of these denominators to an 81. So I have the 1 over 81 minus 2 over 81 times the quantity 8x over 9 plus 3 over 81 8x over 9 quantity squared minus 4 over 81 8x over 9 quantity cubed. So these are the first four terms. So here's my first, second, third, and fourth terms. Now remember, when you write your second term and your fourth terms, don't forget to bring the negative with that. Now in my math lab, that's how the answer appears. We could go further and simplify it. I think they're leaving it in this form and not reducing any of these is because this 8x over 9 is showing where this term comes from right up here. So I think that that's why they're doing that. But if you wanted to simplify it, you could, but I think this is a fine solution right here, and that's what I'm seeing as solutions in my math lab. So I have 1 over 81, okay, minus 16 over 81 times 9 is 729x, plus, let's see what we can get to simplify here. 8 squared is 64. 64 times 3 is going to be 192. X squared over, and this is going to be 81 times 9 squared is 81, minus, here we'll have 8 cubed, which is 512 times 4 would be 2048, so minus 2048 x cubed all over 81 times 9 cubed, and 9 cubed is 729. So let's see if we can simplify any of these further. So for obviously the first term, 1 over 81 doesn't simplify. Negative 16 over 729, the factors of 16 are 1, 2, 4, 8, and 16, and they do not go into 729, so 16 over 729x does not reduce. Then here I have 192x squared over 81 times 81. I'm not going to actually multiply that out. Let's show how that cancels right here partially. If I add up the digits of 192, I get 1 plus 9 is 10 plus 2 is 12. 12 is divisible by 3, so that means 192 is divisible by 3. So if I take 192 and divide that by 3, I'm going to get 64. And if I take one of these 81s and divide it by 3, I'm going to get 27. Okay, so that's how that first or that third fraction simplifies. And then next I have minus 2048 over 81 times 729. So let's see what we can reduce there. Now this numerator are only powers of 2, so 2048 is 2 to the 11th. So this is just 2 times 2 times 2, etc. until we have 2 to the 11th. None of these numbers in the denominator are even, so I don't have anything that I can cancel here. So this is going to be minus 2048 x cubed over 81 times 729, which is 59,049. So rewriting one more step is 1 over 81 minus 16 over 729x plus, then we have 64 over 27 times 81 in that denominator, and I have 2187 x squared minus 2048 over 59,049 x cubed. So that would be another solution, but I like this one up here, and my math lab will accept that just fine. So that might save you a little bit of time. As usual, if you have questions, let me know. Make sure you use those Taylor series tables when they're in a homework question. They'll help you out a lot. It'll save you from having to take those derivatives and evaluating them and writing out your own terms in series. So good luck, and please let me know if you have any questions.